Hi students, today we are going to talk about NMR spectroscopy. Basically, we are talking about the question and answers only. Let me just talk about the quickly what is exactly the NMR spectroscopy. Now, this is a basic principle of NMR spectroscopy that any nuclei which is having half integral spin, particularly the nuclei, if we talk about a proton, if you see here, C13, fluorine, phosphorus, these are the nuclei which are normally targeted for NMR spectroscopy, which is having half integral spin. Now, such nuclei which is having half integral spin, when they spin at their own axis, they induces their own magnetic field. When they place in a strong magnetic field and irradiate with the radio frequency, what will happen? The nuclei itself arranged with the magnetic field and against the magnetic field. So there will be two fields like this. So with the magnetic field plus half and against the magnetic field minus half. When the radio frequency irradiated with this nuclei, which is having half integral spin, they absorb the light, and some of the light will be absorbed for the flipping of the spin, and that absorptions of the radio frequency by the nuclei, which will be showing some signals in the NMR spectroscopy. And that signals is vital information in terms of structural elucidation, structural informations. Now, what exactly this NMR spectroscopy, like the nuclei which is having half integral spin, when spin at their own axis, they place in a strong magnet, they themselves arrange with the magnetic field against the magnetic field and the radio frequency. When irradiated, some of the light will be absorbed by the nuclei, and each set of the nuclei will give the different informations. And in fact, the proton is targeted here. So we call as a PMR, proton magnetic resonance. If it is a carbon, then we call as CMR. Mostly, these two techniques are most powerful to study the NMR spectroscopy. Now, going a little bit ahead, particularly just to understand this concept in detail, let me show you some diagram below related to the same questions. Let me get the next page. Look at here. So this is the nuclei, which is having half integral spin. When they spin, in the beginning, they are randomly moving. When they place in a strong magnetic field, some of the nuclei are with the magnetic field and some are against the magnetic field. So this will be the loss of degeneracy. Here there is a degeneracy, and here there is a loss of degeneracy. Means there will be two energy levels, and that two energy levels definitely will serve the purpose of NMR spectroscopy. In fact, spectroscopy technique is interaction of light with the matter, and that matter contain different energy levels. But in case of NMR spectroscopy, we're talking about the spin orientations, and that spin orientation is studied with the help of NMR spectroscopy. This is the brief introduction about these questions. So you can see all the details are mentioned over here. So mostly the nuclei which is having the half integral spin, they are NMR active. So this particular first point is very important. If there is a we can say here, sum of the protons and neutron is even. So the integral, that spin quantum number will be 0 to 1, 2, 3. So such types of spectroscopy, particularly in case of the C13, the deuterium will show the peak. But whereas in case of proton NMR, it will be inactive. Whereas if both proton and neutrons are even, then the I will be 0, and such nuclei are not at all studied in NMR spectroscopy. This is all about these questions. Let's move on. The important part of other questions. So let me just rub it out so it will move on my next page. So I'll go to the next questions, which is very important. That most of the time the questions will be asked on write the number of signals or equivalents and non-equivalent protons in the following given sets of molecules. Now, in case of NMR spectroscopy, as I told you, the group of proton which are equivalent, like take the example, I will tell you the equivalent and non-equivalent proton first, and then we'll move on to these questions. Like take the example, this is CH3, CH2. Okay, so I have asked the questions also. This is CH3, CH2, and this is OH. Now here there are 3 protons, here there are 2 protons, here there is a 1 proton. Now these 3 protons are equivalent, these 2 protons are equivalent, this one is there. But this one and this one, they are not equivalent. So they are non-equivalent protons. So these equivalent protons will show the one signal, another equivalent protons will show the another signals, and this OH will show the another signal. So that means in case of ethanol, you will find 3 peaks, or we can say 3 signals. Okay, so it is denoted by some kind peak or maybe the signals. Like take the example of methanol, CH3OH. Now here there is a 3 equivalent protons and there is a 1 another proton, but these 2 protons are non-equivalent. So there will be 2 peaks or 2 signals. Take the another example, ethyl methyl ketone. So this is ethyl ketone and this is methyl group. Now in all, this set, and this set. So there are 3 different sets of proton. So that means 3 peaks you will be getting in NMR spectroscopy. That is we called as low resolution spectra. Okay, so this is just we are talking about number of signals in the following molecules, or we can say equivalents and non-equivalent protons. So equivalents are 3 over here, 2 here, but this 3 and this 2, they are non-equivalent. These 3 are equivalent. So this is the meaning of this. Let's move on to the next slide. Let me just get rid of with this stuff. Clear all. Let's move on to the next example. So this ethyl methyl ketone is already we have discussed. Now look at here. Most of the time they will ask you, they will give the structure some point, they may not give the structure. So you need to draw the structure first, and then you have to identify how many signals or peaks will be expected for so and so molecules. Now this is 1-propanol. 1-propanol, you have to write the propanol structure first, CH3, CH2, CH2, OH. So now how many carbons are there? 1, 2, 3. So propane, OL, that means your alcohol. So no doubt there will be 1, 2, A, B, C, D. So 4 signals you will get. Now if we have 2-propanol, so structure will be something different. So the position of the OH group will be different. So this CH3 and this CH3 will have a symmetry. So this will be A, this will be A, this will be B, and this will be C. So there will be 3 signals or 3 peaks. Okay. Now propanol. Most of the time students get confused with propanol and propanol. There is a slight difference between the spelling of this AL and OL. So AL stands for aldehyde. So that means this will be CH3, CH2, CHO, aldehyde. Now 3 different peaks will be there for this one, another, and another. So you can refer this A, B, C. So there will be 3 signals. Butanol, again same. So you can draw the structure CH3, CH2, CH2. Again, this is aldehyde. So this will be CHO. Now, no doubt this will be A, B, C, and D. 4 signals will be there. Butanol. Now, This is alcohol, CH3, CH2, 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 OH. Now, how many peaks will be there? 1, 2, 3, 4, and A, B, C, D, E. So 5 signals will be expecting for these molecules. Now, N-propyl bromide, that N means normal straight chain. So this will be the CH3, CH2, CH2, and this will be your Br. Now, if you see here, in case of, just let me get something rid of with this. Okay. So if you see here, A, B, C. So there will be 3 signals. Now isopropanol. So that means there is alcohol, but the position of the OH is on second. So this is your isopropanol. So this and this having the symmetry. So this will be A, this will be B, and this will be C. So there will be 3 signals for isopropanol. Some point, if the structure is given, it is very easy to draw the number of signals or peak for such molecules. But if not, then you have to draw the structure through the names. I have a couple of lists more. I will get a couple of questions. Just get me rid of with this. Delete all clear. Then I can move on next. So this is another slide. You will see a couple of more structure. Now, methyl benzene. This is also called as toluene. Okay, some point they may give the toluene as a name, or it may be mentioned as a methyl benzene. So this is a toluene. Now, how many peaks will be there for this methyl benzene or toluene? So if you see here, this CH3 will be the A proton. Now this proton and this proton is same. This one and this one is same, and this one is different. So total A, B, C, and this will be D. Now here this will be C and this will be B. So there will be 1, 2, 3, and 4. So this is, and this one is same. This one is same. So this one is, so 1, 2, 3, 4. 4 signals will be for the toluene. Now ethyl methyl ether, it is exactly same as that of ethyl methyl ketone. So exactly same. So this will be 1, 2, 3. Xylene. And there are 3 structures of xylene: ortho, meta, and para. We will draw here the structure systematically at once, all 3 structures together. So it will be easy for you to comment on these molecules. So I'll write in a row all 3 structures. Now xylene means 2 methyl group. Okay, so this is first is your paraxylene, means both the methyl groups are 1,4 position. Another one is 1,3 position. Another one is 1,2 position. Okay. Now look at here. This molecule will have symmetry, straightaway symmetry. So you have to take the half of the proton in consideration, because they will overlap and their peak height will be more. So this will be A, this will be A. Suppose this will be B, B, and this will also be. So this will also be. So total 2 signals are possible for this. Now, if you see here metaxylene, there is a symmetry, but this type of symmetry. So this A and this A, this will be B, this will be C, and this will be D. So total 1, 2, 3, 4. 4 signals will be possible. Now here there is this type of symmetry. So this will be A, B, B, C, C. So 1, 2, 3. 3 peaks are possible for the orthoxylene. So there are 2, 4, 3 peaks. For xylene, there are only 2 peaks. For metaxylene, there are 4 peaks, and orthoxylene, there are 3 peaks. Let's see the structure of ethyl acetate. So you should know the structure. Okay, so acetate means this group, acyl group, and E OET. Okay, so that is ester. So this ethyl acetate. So this CH3 and this CH3 is not same at all, because this is attached to the CH2 and this is attached to the carbonyl. So this will be A, this will be B, and this will be C. So there will be 3 signals for this molecule. Now acetophenone. So this is again ketone, but there is an aromatic ring attached. So this will be like this structure. So the CH3 will be the 1A. No doubt this orthoproton will be same, meta will be same, and this para will be different. So A, B, C, and D. So this will be C, this will be C. 1, 2, 3, 4 picks for acetophenone. Methyl propionate. Most of the time they will ask you sometimes different questions like how you will differentiate between ethyl acetate and methyl propionate. So the structure of the methyl propionate is exactly opposite to this. So ethyl group will be to this side, okay, and then methyl group will be towards attaching to the O. So this is your methyl propionate. So exactly the same structure, means same peaks as that of ethyl, but the splitting pattern will be different. Their del value splitting pattern will be also same, but the del value will be different. So that we will see later. So this is your A, B, and C. So 3 picks for this. Now another important is vinyl chloride. You know the vinyl chloride. Most of the time, students get confused for this vinyl chloride. How? I will tell you that. Now, most of the time, we do write the structure for vinyl chloride like CH2. Let me get the pen. CH2. Double bond CHCl. Now, normally we get confused that this will be 1, 2 peaks. But whenever there is a cyclic structure or the olefinic structure, we have to write their geometry. And that geometry will have a different environment of this proton. So these 3 protons, like take the example of A, this will be B, and this will be C. Why this is different, this CH2? Because this hydrogen is away from the Cl. This is close to the Cl. That means this is cis to this is trans to this. So that's why this and this are different proton. So altogether there will be 3 signals for vinyl chloride. So this is the signals for vinyl chloride and the different structure. We have included aromatic, ketone, aromatic, hydrocarbon too. Let's move on to the next. We have a couple of structures more. Like these are all questions normally asked in the university exams. Now 1,2-dichloromethane, like methane. So that means this is CH4, but there are 2 bromo group attached to 1 carbon. So I will write here Br to this side. Sorry, this is ethane. So this will be CH2, CH2, and this will be Br. Okay, so this is completely wrong structure I have drawn. So here this is, the position is 1, 2, 1, 1. So this is 1, 1. So at 1 carbon only, we are having both the bromide attached. And another one is 1, 2. So this is Br attached to the CH2, CH2, and Br. That means this is 1, 2, this is 1. So this is CH3, 1, 2. So these bromides are attached to the 1 carbon only. This is 1, 2. Now here, look at here. This is 1 peak, this is another peak. But here for this, there is symmetry. So this will be A, this will be B. So this will be 1 signal and this will be 2 signals. So this is all about the number of signals in case of the name of the structure has been given, and just write down the number of signals or peak. So this is such a simple topic. and mostly scoring one in terms of the university exam. Let's move on to the next questions, which is frequently asked in the examinations. What is chemical shift? In NMR spectroscopy, what is chemical shift? Chemical shift is what? It is nothing but the distance between, this is your standard reference, this is zero, called as TMS. The distance between the standard and the peak observed is called as chemical shift. Now the standard is TMS, which is extremely right hand side of the spectrum, which is considered to be zero. From zero we have to count the del values. So this is a distance between the standard and peak observed. If you write like this only, the distance between the standard TMS and the peak observed in the NMR spectra is called as chemical shift, which is measured in del value. It is measured in del value, which is ranges from 0 to 14 in case of PMR, that is proton magnetic resonance, because in CMR the del values are completely different. Now, how to calculate this chemical shift? That simple formula is given here. We are going to talk about that. Now, this is the sample frequency minus reference frequency. That means the frequency of this is your reference and frequency of your sample. So if you take the difference of these two, divide by the reference, that is your instrumental frequency, into 10 to the power 6, that gives you the del value. We'll describe in detail what exactly this del value calculation and other. So in short, what exactly the chemical shift in NMR spectroscopy? The distance between TMS, that is standard in NMR spectroscopy, and the peak observed, this distance is called as chemical shift, which is measured in del. Okay, which is measured in del. In PMR, it is ranges from 0 to 14. If you want to write this formula, will be appreciable. If not, draw this spectrum, any simple spectrum, need not to mention the name or sort of things, but only thing, simply you can draw like this. This is your TMS 0 and the peak observed. This distance is called as chemical shift, which is measured in del. So that is all about this chemical shift in NMR spectroscopy. Let's move on to the next questions. Okay, this is interesting one, but very simple. What is TMS? Just now we have spoke about in terms of this example that TMS is what? Standard. So what is TMS in NMR or reference standard in NMR? Both are the similar type of questions, but they may ask what is TMS in NMR or maybe the reference in NMR. So TMS, that is tetramethylsilane. That means silane is Si and 4 methyl groups are attached to one element called as Si. And here there are 4 methyl groups which are equivalent, and 12 protons are attached to this particular TMS. Now, these 12 equivalent protons will give the sharp peak at extreme end of the your NMR spectrum. And because of the electropositive nature of the silicon, electropositive, okay, which is electropositive, that's why it is on extreme right-hand side. If you see here, your carbon, your proton, which are more electronegative than the silicon. So that's why the values which measured in del value, they are away from the zero, and that matters in case of the TMS. So most of the peak which are away from the zero, they are more electronegative. Towards zero, they are, we call as electropositive, but they are not fall under like silicon categories. So that's why we refer this as a standard. What are the chemical properties of this TMS? It is chemically inert. It doesn't react with any compound. It is volatile. It can be easily off. It can be removed. It has a symmetrical structure. It is non-toxic, and it is easy to handle in terms of getting the sharp 12 protons peak in NMR spectrum, and which is recorded at 0 ppm. Here NMR del scale is your we can say the unit which is measured in parts per million. So that 0 is your reference, that is your TMS. So this is the question. Now another question frequently asked in the NMR spectroscopy: what is a solvent in NMR? Now, what solvent we do use? We do not use a protonated solvent. Like take the example of ethanol. We cannot use ethanol as a solvent. Why we don't use ethanol as a solvent? The reason behind, the proton of this ethanol will interfere in the study which compound you are targeting for their your interpretation. So this peak should not interfere. So we do use deuterated solvents. That means the hydrogen will be replaced with the deuterium, and deuterium spin is 1. So the 1 spin in case of proton NMR will not show active peak. So that's why the peak of the solvent will be dropped in the PMR, that is proton magnetic resonance, or we call as NMR, proton magnetic resonance. So the deuterated solvent like CdCl3, that is a deuterated chloroform, deuterated heavy water, deuterated methanol, chloroform, sorry, your CCl4, CS2, that is carbon disulfide, that is deuterated toluene, deuterated DMSO. There are many solvents which use in NMR spectroscopy. So basically, you have to keep in your mind any solvent where there is a proton, they cannot be used. The proton should be replaced with the deuterium. That is the main condition. So deuterated solvents are used in NMR spectroscopy. This is such a simple question. Move to the next questions. What is integral height in NMR spectroscopy? Now, we're talking about the TMS and the observed peak. Now, we're talking about the height of the peak. So this is one of the application of NMR spectrum. What that? The integral height of the peak. The height of the peak, like take the example, I will tell you, if there is a like methanol or just one CH3 group, I will just mention here CH3 group, and there is a one compound which is having 2 carbon atoms, like 2 CH3 groups attached to 1 carbon, means that CH3s are symmetrical. Now if I wanted to see the peaks of this particular 2 compounds, 2 protons in NMR spectrum, so the height of the spectrum, like take the example here. Now if I would say CH3, the height will be this. If there are 2 CH3, the height of the peak will be double. So this integral height will be equals to 6 proton, and this integral height will be equals to 3 proton. That means height of the peak in the NMR spectra is directly proportional to the number of proton. Like take the example here, this B is having 3 protons, so the height is more, and this is 2 protons, the height is less. So this is we call as integral height. So this integral height is for 1 proton, and this integral height is for 6 proton. So the integral height is directly proportional to the number of hydrogen atom present. So integral height of peak or area under peak in NMR spectroscopy represent the relative number of protons contributing to each signals, and it helps to determine the ratio of different types of hydrogens in different environments, which helps in determining the structure of the molecules or exactly the number of proton present in that molecule. So this is what the integral height in NMR spectrum. Move on to the next. What is shielding and deshielding? Now we were talking about, that is, there is a TMS, that is a standard, and this standard is extreme at the right hand side of the spectrum. Now the observed peaks are away from the 0. Now how far away? So this how far away means the number of del value, whether it is close to 0 or away from 0, that means maybe in the bigger number. So that number is related to the shielding and deshielding phenomena. Now this is requires some of the basic knowledge of the NMR spectroscopy. I'll tell you how this is explained. Now look at here. When the nuclei, as I told you in the beginning, the nuclei when spin at their own axis, like take the example of this nuclei, when it is spinning at their own axis, it produces magnetic field. Now this magnetic field may be north or maybe the south. Okay. And the applied magnetic field is supposed in the same direction, north and south and north. Then what will happen? Both the magnetic field have the same lines of forces. That means in simple language, when you are going towards the like you are riding the bicycle and you are getting the wind in the same directions, the energy required for the pedaling your cycle requires very less energy. Why? Because the wind will pushing you. So in a similar language, similar phenomena, when the magnetic field which is induces by the each nuclei when they spin at their own axis, if their magnetic field is having the same direction to the applied magnetic field, this is your applied magnetic field, then what will happen? The required magnetic field will be less. And such nuclei required lesser amount of magnetic field. Now I'll tell you here, what is del? Del is nothing but the ratio. What is this ratio? The difference between the frequency of your observed peak, and this is your instrumental frequency, and this is 10 to the power 6 for converting it to parts per million. Now what I'm trying to explain you, if your del value is very high, like high means away from zero, like take the example, it is 10 and it is like 1. Which number is bigger? The 10 number is bigger. Now in simple calculation or simple mathematic calculations, if the denominator is less number, then this del value will be more. If denominator is less, that means applied magnetic field is less, del value will be more. Suppose for 10 number of this del value, the required magnetic field will be less. That means this denominator will be less. If for the 1, if I wanted to go towards 0, the magnetic field required will be more. That means if the peaks are towards the 0, we call as these protons are shielded. These protons are shielded because they are towards 0. If the peaks are going away from the 0, then we call as the deshielded. That means higher del value. This is higher del value, and this is lower del value. Now lower del value will be shielded, higher del value will be deshielded. That means higher del value requires lesser magnetic field because of this formula. Denominator, if this is less, this will be high. This is straight away calculation. So shielded protons requires higher magnetic field, they are towards 0, and towards away from the 0 will be deshielded. Now here, who makes this proton to be shielded and deshielded? Like take the example, this is some proton having the electronic status. And if I have any electron withdrawing group attached, so the electron withdrawing group will withdraw the electron from this of the nuclei. So that means the nuclei will be withdrawn by the electron withdrawing group. So in that case, such nuclei is considered to be deshielded, and those nuclei which are having electrons but the group attached does not affect, like CH3, it does not withdraw any electrons. So such nuclei, such protons go towards 0. That means they are shielded. So electron withdrawing group makes the shielding and deshielding effect. So that means whenever there is a electron withdrawing group in the process or in the system, the protons are deshielded. They require lesser magnetic field. Those having less electronegative atom like CH3, they are having a del value more. That means they are shielded. So in simple language, how you will understand this phenomena, the NMR spectroscopy shielding refers to the protection of the proton by surrounding electron density, causing them to experience weaker magnetic field and appears a field that is a lower value of del values. That means these are upfield protons. And such protons are we refer as a shielded one. Okay. Now deshielding occur when the electrons are withdrawn by the electronegative group and by nearby the magnetic effects, exposing protons to stronger magnetic field. That means they are shifting toward the down field. So this is a down field and this is up field. That means up field means more magnetic field required. Down field means less magnetic field required. So this is a simple meaning of the shielded proton and deshielded proton. Meaning shielded is required more magnetic field. Deshielded means required lesser magnetic field. Like this denominator required is less, that means del value will be more. And why it is possible? Because of the electron withdrawing groups or atom present in the system. So this is what the shielding and deshielding phenomena. Okay, so this is, I suppose, easy to understand you people. Now, what are the things which affect the chemical shift value? Now, what is chemical shift value again? So let me talk about chemical shift value means the distance between 0 and peak observed. This is called as chemical shift. Now this value, whether it is towards 0, that is 1 or maybe 10, how it depends? It depends on, as I just now talk about shielding and deshielding phenomena. So this will be caused by electronegative atoms. So chemical shift is affected by electronegativity. More the electronegativity, more will be the deshielding, and the peak will be going towards the higher del value. So this is the first phenomena. Second phenomena is hybridization. Now, if you talk about hybridizations, there is a similar type of effect like sp2 hybridize and sp3 hybridize. Which one will be more electronegative? No doubt sp will have more s character, so they are close to the nucleus, so this will be more electronegative. And obviously if there is a more s character, there will be more del value. So this is another effect. And there is a anisotropic also supporting for hybridization process. So that we'll talk on later in detail. But electronegativity is one thing, another one is hybridizations. More the S character, more will be the electronegative. So higher will be the del value, they will be deshielded. That means downfield. Magnetic anisotropy. Magnetic anisotropy is nothing but like if we having some system having a proton. Now this proton will induces magnetic field. This proton, when induces magnetic field, they will be placed in a strong magnet. Okay. And if they are suppose with nearby any pi system, so this pi system will have also ability to produce some field, and this field will support this proton to be pushed towards the similar direction to the applied magnetic field. That means, again the same example, you are riding a cycle and there is a wind in the same direction. With that, there is a one friend which is pushing physically. That means this is another friend which is pushing physically. That means the required magnetic field for this proton will be very less. If the required magnetic field is very less, that means the applied magnetic field required less, means denominator is less, means del value will be high. So magnetic anisotropy gives you the unnatural phenomena which is supporting to the induced magnetic field of this nuclei to be so to be predicted in the NMR spectrum to the higher del value. That means this particular magnetic anisotropy will be caused because of the some ring current or the pi electron current which push the proton in the similar direction to the applied magnetic field. That means there is a reinforcement, and that reinforcement will cause the lesser magnetic field for the flipping, and that's why the del value will be higher, and that comes under the magnetic anisotropy. We are going to discuss in details with the context to the aldehyde, aromatic ring, and olefinic and acetylene compounds. Another one is affecting the hydrogen bonding. You know, the hydrogen bonding, when the proton is trapped in between the two electronegative atoms, like maybe the nitrogen or maybe the oxygen or fluorine. So that means this proton will be having the higher electronic environment, and definitely in such case the del value will be higher because applied magnetic field will be less. So this is all about the factor affecting. There are the four factors: electronegativity, hybridization, magnetic anisotropy, hydrogen bonding. So these are the four factors which affect the chemical shift value. That means they increases the chemical shift value in all. There is a one example, that is magnetic anisotropy. In case of the hybridization also, that sp hybridized acetylene will have less del value because of some orientation. We will see that later on. So this is all about your factor affecting the chemical shift value. Now let's see the questions related to that. Now suppose we have this system where question is like this: compare the chemical shift values of methane. Then we have another system called as chloromethane, methane, chloromethane, dichloromethane, trichloromethane, that is chloroform. Now look at here. In case of this, the del value is 0.2, or it because it is a CH4. There is no any effective group. It is not attached to the carbon. But if there is a one Cl group attached to this nuclear carbon, having this nuclear proton, this will be influenced greatly because of the electronegativity of Cl, and this del value will be 3 ppm. Now, if there are two Cl group attached to the same carbon atom, the influence of these two Cl group will be more. So the del value will be much more higher than this. So the required magnetic field for this will be less. As the electronegativity goes on increasing, the required magnetic field B0, that is denominator, will be less, and the del value will be more. So there are three Cl group attached to the one carbon atom. So the proton attached to that will resonate at 7.1 ppm. So here there is a great influence of the group attached, the electronegative group attached to the carbon having the nuclei. So as more electronegative groups comes in, the electronegativity will directly influence the proton, and there is a deshielding effect, and that deshielding effect will increases the del value exponentially as the electronegative group attach. So this is clearly mentioned here. This is the example to explain this. Now let's see the next questions. Why? Okay, what is the questions? Oh, something is wrong. Compare the chemical shift. Oh, this should not be there. Compare the chemical shift value of CH3 group, okay, in chloromethane, chloroethane, and 1-chloropropane. Okay, so CH3 group attached to the chloromethane, chloroethane, and chloropropane. Now look at here, the position of the CH3 group attached directly to the Cl here. This CH3 is having in between CH2. That means there is a barrier in between the electronegative atom. Here there are the two CH2's barrier. That means this CH3 and Cl, they are away from the electronegative effect. So this del value is 0.9. This one is 1.4. Where it is directly attached, it's 3. That means how to compare this? This comparison is straight away as the distance between the electronegative atom and the nuclei under study increases, the del value will decreases. This is straight away the answer for this. So the answer is given in the next line, I suppose. Okay. Now this is all about for today. Definitely we will be discussing the another questions in coming lecture. Just go through this whatever discussions we have done so far for the 10 questions. The more coming lectures will be basically on solving the problems, combined problems, and anisotropic questions. Magnetic anisotropy, there are a couple of theoretical questions, and then there are combined problems which will be like major components in the examinations. So don't miss the next lecture. Just subscribe this channel and you will definitely get the signals for that lecture. And whenever, maybe in couple of days, I will make more lectures online, and it will be useful for you before your examinations. Thank you very much.